Hello, great to be here today. Thank you very much to the organizers for inviting me to give this presentation today. My name is Kaspar Althoefer and I'm from the Center for Advanced Robotics at Queen Mary. And in my presentation today, I will look at how we can advance sensors to measure, to perceive touch, in particular for collaborative robots. And I will particularly look at new sensing technologies that are suitable for soft robots, which are particularly useful for collaboration with humans. And in this context, I have to say we have experienced quite a shift from the cage type of robot, as we can see it here. So very, very common appearance in manufacturing environments where these robots have been very successful in carrying out the tasks that they were required to do. However, most of them are behind fences, away from humans, because they are made from rigid components and as such very dangerous, not safe for human collaboration. And so there has been a shift now to something much more soft, and also moving towards new application areas. So for example, using soft robots now to support the elderly or disabled, as indicated by this bionic soft arm shown in the image. So there have been a number of approaches recently to create now soft robotic structures, as we can see here in these videos, for example from Harvard, but also from us, from Queen Mary. You see the octopus on the bottom right side. But I would like to highlight this system shown on the bottom left, an industrial system, so a product already using the soft robotic principle. So we have here a soft structure made from silicone rubber, pneumatically actuated, and very capable, as we can see, in picking up a number of different objects as required for manufacturing tasks. And here a few more examples. So for example, on the top left, our soft robotic hand that we have developed for use in prosthetics, especially for children. And as you can see, we can achieve very natural movements with these kind of devices. Similarly, natural movements can be achieved with this robot finger made from fabric and inflated, pneumatically inflated by air. And so we have quite some maneuverability here, and above all, devices that are capable now of interacting with humans and be used in the collaborative sense. Another example is this robotic device here that is also made from soft materials, and it's capable of carrying out a task. So in this particular case, to pick up a ball. That could be something useful in an assembly task, and they are very reliable in their performance, these kind of robotic devices, and cope quite a bit with variability. So, however, these devices need to be able to sense the environment in order to act accordingly and react to the environment, carry out meaningful tasks. And so I've been looking into the current kind of situation, and here we can see the standard approach to robotics that has been the standard up to recently, definitely. So we have rigid component robots, and they are very easily equipped with a range of sensors. So for example, we have force torque sensors, we have position sensors. These are now rigid components that can be easily attached to the rigid components of the robotic device. We use inverse kinematics, so have simple models to describe these devices and carry out the required tasks that are often dictated by the manufacturing environment where these robots are being used. And So we think here about very simple environments, very predictable environments, and these tasks can be effectively planned without any problem. So that summarizes that again in a different viewpoint. So we have the world here on the one side, we sense it with our sensors, and then there is some software there that makes sense of the sensors and reacts or sends commands to the actuator so that the device, the robot, can react in the right way. And that is controlled by a user that is behind there and is informed obviously about the more high-level tasks that need to be carried out. And this approach is very much in the traditional sense based on simulations. So you have models, you can plan everything before you actually carry out the tasks. However, if we now move to the world of soft robotics, we can see that there are a number of challenges. And what is most important, it is now very difficult to integrate these standard sensors that we are familiar with. So for example, force torque sensors that are made from metal parts and are capable of measuring forces and moments when the robot is in contact with the environment. And I have this focus on soft robotics because I believe they are very suitable for this particular task, collaboration, human-robot interaction. So if we now look at these new sensor requirements for these type of robots, then we recognize, and on the one hand we have these rigid component robots with the particular sensors that are useful there. Now we need to look at the soft counterparts, and that's where the challenge really comes. So there have been a number of approaches over the years now to create now new sensing technologies for soft robots. And I'll show just some examples here. So we have resistive approaches, so where systems are being created, sensors being created, that when actuated, when strain is applied, have a resistive behavior, and in this way we can then measure, for example, the forces applied. Piezoresistive is another example, and Ravinder has worked in that area, of course, quite a lot. And so I have him here with one of his works on a tactile sensor, a flexible tactile sensor included. But there are other approaches. Capacitive is quite widespread. There are magnetic approaches, also piezoelectric approaches that have been used in this context. This is by all means not an exclusive list of all the sensing approaches that have been used in the context of soft robotics, but just to give you an idea on the different methods that are being investigated. So here, just to go over a number of different types of sensors. So here, for example, an embedded resistive strain sensor for estimating the pose. So we have a strain sensor now that is integrated with a robotic device, in this case a robotic hand, and this can be then used to measure the strain along this sensor, and then from that we can compute the bending in this particular case. Other approaches look at capacitive elements that are being integrated. Here in this particular case by BKI, we have a sensor made of silicon material or integrated with silicon material that is capacitive and can measure now forces along 3 axes within that flexible structure. Another interesting approach to sensing interaction with the environment has been proposed by Brock and his team from Berlin. And in this particular case, we have the possibility now to measure interaction with the environment through a microphone. So a microphone is integrated with the flexible structure, with a soft structure, in this case a soft robot hand. And the advantage here is that we effectively can do a contactless sensing from the interaction with the environment. Other work looks at e-gain, so a number of researchers have looked at using this kind of liquid type of resistive material to measure now interaction forces in very soft sensors. We can see here an example of a silicon embedded sensor using e-gain, and as you can see, the sensor is very flexible, very stretchable, and we can measure now forces that are imparted onto the structure, but we can also measure the the stretch of the sensing material. This is work by Robert Wood from Harvard University. Now, we have looked at Queen Mary quite a bit into optical-based sensors and have used those for tactile exploration. So we have quite some kind of experience there in that area, and so here's an example of an optics-based sensor where we have integrated optic fibers with a deformable structure. And when the structure is now being deformed because a force is applied from the outside, the light that is shown by the fiber, by one of the fibers onto this deformable structure is changed. And when I say changed, what is changed? The light intensity is being changed by the forces applied, and that is a relationship which we can then use to effectively identify the forces that are being applied from the outside. So we shine light onto the deformable structure, receive light back through a receiving fiber, and from that information, the light intensity, we can then compute the applied force from the outside. And in this particular case, we were able to move towards a 3-axis sensor, 3 degrees of freedom, so we can measure X, Y, and Z information. And that is integrated, in this case, into a structure that is 3.2 millimeter in diameter and suitable for the exploration of the inside of the heart. So we can measure, if that is attached to a catheter, the interaction between the catheter and the heart wall, and that is very suitable for electrophysiological studies of the heart for patients with arrhythmias, for example. What I find particularly interesting here in this work is that we are making use of a vision system, a camera, in this case actually a very simple camera. We can use the camera to receive the light from these fibers, in this case 3 fibers for the 3 degrees of freedom, and we can interpret then these images through some image processing programs, and that allows us then to effectively from the images to compute the forces, the 3-axis forces applied at the tip. Also created integrated fingertip sensors, so we can see here a fingertip, a robotic fingertip that was integrated with a robotic device in the framework of an EU project called Squirrel. And we were able now to integrate multi-degree of freedom sensors with the tip of these robot fingers. Again, 3-axis we were able to measure, and that allowed us to measure the interaction between fingertips and the environment. I would like to add here that we were also able to integrate proximity sensors, and we can see them here in red. And having now proximities, so I should add, these proximity sensors are based on the same principle that we use for our tactile and force sensors. Hence, it is based on light intensity. So you send out a light beam that is reflected by an object nearby, and depending on the distance between our fibers, our pair of fibers, and the object, we can actually measure now the distance to objects. And now if we combine that, I hope this video runs now, yeah. So if we combine now these force sensors together with the proximity sensors, then we can actually not only measure tactile and force information, but also estimate the stiffness of the object that our sensor is in contact with. So our fingertip here is now pressing onto this foam, and you can see the red lights. These are actually these are the proximity sensors. That combined with the force information allows us to measure the stiffness of this foam material in this particular case. However, we have been also looking into integrating our sensors into soft robotics, and that has its origin in a project, EU project called StiffFlop, where we were looking at integrating our sensors, our optic-based sensors, into structures like these. So we can see here a multi-segment flexible soft robot made from silicon material moving inside the mock environment of a patient. It's a phantom, and as you can see in the top left, we have images being fed back by the integrated camera. So this is now a robotic finger made of 2 segments, each individually actuatable through pneumatics, and we can move this finger around now in this environment. And to enable now an understanding of the interaction with the environment, we have integrated a number of sensors, tactile sensors, force sensors, and also bending sensors with this device. So, for example, pose sensing. Here are now some of the examples, again based on the same principle. We are using now our fiber optics, and they are integrated now with this device. And the more we bend in one or the other direction, the more light intensity will be changed, and that can be then used to effectively understand the pose, the amount of bending and the direction of bending of our robotic segment, as you can see here. So we can see the robot finger in the foreground, and in the background is then the visualization of the data that we receive from our sensors. As have been explored, so here we are now looking at, again, integrating force information, force sensing information, try to measure force sensing information from our robot finger. So here we have force sensors integrated with our robot finger, and you can see that here in action. Now the force sensor is actually at the base of this finger, but forces are transmitted through the flexible material and can then be recorded and recognized. We have been also very much inspired by recent work by Robert Shepard, which we can see summarized here. So this is moving a step forward, so not using standard optic fibers, but actually to create optical waveguides that can carry light, but are super flexible. And when they are bent, when they are stretched, the light intensity is varying. And that has led to recent work in our place, whereby we integrate now these transparent waveguides into our robot soft fingers. And the idea is now to estimate the pose that the finger has, but also to estimate the forces that are being applied from the outside. Now, there are also other approaches that one can take, in particular when looking at soft robotic arms and other devices. So our work here has been focusing for quite some time on variable stiffness links. So the idea is to integrate robotic arms with these kind of links which are which can change their stiffness. So they are particularly suited for human-robot interaction. So as you can see, very stiff to start with, but then when the air is taken out, they become soft and very safe. But how can we now measure the interaction with the environment? And here in this particular case, we actually use the pressure sensor that's already built in to control the pressure of our inflatable link and observe what is happening. And when a collision is occurring with a fingertip, as is shown in this example, then we have a peak in the pressure as indicated on the left-hand side. And recognizing this peak, we can then control the robot and take an evasive action. So collision occurs, robot moves away and reduces the internal pressure and is safe. We have also looked at another approach that was in collaboration with colleagues from Japan. Shinichi Hirai worked here with us, and we created a fabric that had a is conductive and could be then double layer system could be created to create a capacitive system, and that allows us then to measure interaction with the environment. So the next step here would be to actually create these stiffness controllable links straight away from the fabric, because that's what effectively they are. They are fabric-based links that can be pneumatically then actuated, or pneumatically we can change the stiffness. Another important aspect is scalability, and obviously we are far away from creating systems that are capable of doing something like that, but we have been taking inspiration also from vision, and so how can we now take what has been very successfully done in vision, so image processing, now also based on machine learning and AI, to actually make sense of the sensor data, and that has been very successful. And we have been now looking in this area as well, and we are looking at camera-based systems. So here we have a flexible structure that is made of silicon material and can be brought in contact with the environment. And we can now use the camera to observe what's happening to this flexible structure. So in this particular case, we have these, the structure with these multiple fingers that can bend locally when in contact with the environment. And here we have taken, of course, inspiration from various places. For example, the tactile sensor is one example, and just to show you, so this is a sensor that has a flexible membrane that is brought in contact with the environment, and through the camera system, then one can estimate the forces that are being applied. And similar work has been done also in the States, and we have here the gel side sensor, and that is similar and is capable now of measuring forces, usually normal forces, but through particular processing of the gels, the gel material, the transparent silicon, one can also identify shear forces. We have now moved that a bit further and have created a vision-based sensor that can not only measure the tactile information, but also integrates using the same vision sensor force information. And in this combined fashion, we have here now our sensor on the left-hand side, the elastomeric component that can measure the structure, the geometry of the object that we are interacting with. And that is then combined with a number of deformable structures to measure the actual forces that are being applied. And both together allows us then to measure force and tactile information in one system. And that is where we are advancing on current work. So we have in this video some examples here. So we can now apply forces onto this the finger, the elastic area, and we can see then the forces that are being shown on the screen. And if I just go a bit further to the right, so we can measure the forces, and that is done directly, but at the same time we can also visualize the interaction with the environment. So as you can see here now, this USB plug is being pushed against our flexible membrane. We can see the structure, the geometry of it, and at the same time measure the forces. So let me conclude now. What are the challenges and future directions? So current soft robotic systems, and also that includes collaborative robots, are there. They are being developed. However, they have limited functionality. There is low maturity, and the work is very much in the infancy. The integration now of these soft bodies, soft robotic devices with tactile sensors and force sensors to create functional robots is still a challenge, is still needed. And in particular, if we want to create useful human-robot interaction systems. I believe that we can make good opportunity by using the structural elements in these systems for sensing and actuation, and vice versa. So systems we have these soft robotic structures, and they are pneumatically actuated. So why not use that also in the sensing domain? So as I showed you in the stiffness variable link, here we can now control we can control the stiffness, but at the same time we can measure the interaction with the environment, looking at the pressure variations that occur when there is a collision. However, the coupling sensor modalities, for example, to measure bending or to measure external forces, is still a big challenge. So there is innovation required, especially also in scalable sensor systems. Miniaturization is clearly a challenge that is persistent. I would like to take the opportunity to highlight very strongly that it's not all work that I've done by myself, but I had a lot of collaborators, and I want to really thank especially the younger ones who have been very instrumental in actually, pushing this research that I've shown here forward. But also there are funding bodies that are to be mentioned. So we had funding from a number of organizations, and we were collaborating with a number of organizations over the past 10 years or so on soft robotics and new sensing technologies. I would like to take also the opportunity to mention something that is very close to my heart, ICRA 2023. So we were successful in bidding for ICRA 2023. ICRA is the International Conference on Robotics and Automation, and in 2023 it will come to London, first time in the UK. And yeah, that brings me to the end of my presentation, and thank you very much. Bye-bye.